Normal distributions are the third and last of the three families of frequently used distributions that we're investigating in this section, and they are arguably the most frequently used family of probability distributions because, on one hand, quite a few stochastic phenomena, and we might as well give an example, many scientific measurements are normally distributed, or at least they're assumed to be normally distributed. Normal distributions then also arise through the very important central limit theorem, which we will discuss later on in these presentations. And that basically means that because the central limit theorem talks about averages, and averages are being taken quite a few times, that normal distributions really permeate all of statistics. However, we also need to remind ourselves not everything is normally distributed. It is often a standard assumption in statistics that a certain phenomenon is normally distributed, but technically that also has to be tested because it need not be true. But those kinds of tests and considerations are beyond what we're going to do here. Okay, so what is the normal distribution? Well, a continuous random variable, which we will denote n sub mu sigma, normal mu sigma, is said to have a normal distribution with the parameters mu and sigma if it's got the following probability density function. It's f sub mu sigma of x is 1 over sigma root 2 pi e to the negative x minus mu quantity squared divided by 2 sigma squared, which is a kind of function that I've weaved into quite a few of the earlier presentations so that we don't need to do too many of the computations here, or at least not worry about them too much. Well, mu can be any real number, and sigma is any positive real number. And something that we will investigate also in a later presentation is the vocabulary here. The parameter mu is called the expected value of the random variable, and the parameter sigma is the standard deviation of the random variable. Those are just names right now, but we will breathe some more meaning into them in a later presentation. Okay, so one of the things that we did in an earlier presentation actually is we sketched the graph of this family of functions, and we ended up with this picture. We're not going to go through all the details here, but basically in the presentation on graphing functions with parameters, we saw that this family of functions basically looks like a every one of these functions looks like a bell-shaped curve. The center of the bell is at x equals mu, and the width of the bell is somewhat determined by the sigma. That is really the meaning, the fact that mu minus sigma and mu plus sigma are inflection points from single variable differentiation. That actually is not the reason why sigma is that important. The reason why sigma is important is because it governs the width of the curve. And well, can we also see at least some of the shape from here? Well, yes, we can, because negative x squared is something that gets more and more negative very rapidly as we get away from the center, and that would mean that e to the negative x squared has to decay rather rapidly, which is what it does. And then if we have a large sigma, well, then the decay is slow, and if we have a small sigma, then the decay is fast, which has a bit to do with the width parameter. That is something that we can also look at in a more dynamical fashion. Mu, well, mu just gives us the center, and so if you track the value of mu as this distribution shifts around, you realize that mu really just places the center of this bell curve at wherever the value of mu is. That also makes sense in terms of what we have learned about shifting, stretching, and reflecting, because if sigma is constant, then this is a function of x minus mu, and mu is essentially just a right shift of the graph by exactly mu units. If we're looking at sigma, well, the effect of sigma is that, as I mentioned, large sigma means that the curve gets flat and wide. Small sigma means it gets tall and narrow. But either way, remember that for probability density functions, the total area under the curve must be 1, and this scaling factor, as we've also mentioned in a previous presentation, the scaling factor that looks rather strange, makes sure that the total area that is under the distribution is always equal to 1. And yeah, then large sigma means it's wide, small sigma means it is narrow. Okay, so the next thing we need to think about is how do we compute probabilities for normally distributed random variables. For uniform distributions, we just looked at rectangles. For exponential distributions, we just computed integrals. As we have also seen in earlier presentations, or at least as was mentioned, e to the negative x squared is something that doesn't have a nice antiderivative, so we need to think of something here, and the first step is that we're going to take an arbitrary normally distributed random variable with mean mu and standard deviation sigma, and we're going to just look at the probability that such a random variable takes values between a and b, and of course that's just the integral of the density function from a to b, and the problematic part here is that we've got parameters inside the integral. Let's see if we can get rid of those. The first step is just very simple algebra. We keep the factor out front, and we rewrite the exponent and realize that x minus mu quantity squared divided by sigma squared is, of course, x minus mu divided by sigma quantity squared. And to get rid of this term here, we can just do a very simple linear substitution. Z equals x minus mu divided by sigma. That would give us dz dx is 1 over sigma, and then dx is sigma dz. The x minus mu over sigma becomes z. The factor out front stays the same. And the boundaries, of course, here's one of the situations where we need to remember that when we do substitution with a definite integral, we can just transform the boundaries, and certainly, well, when x is a, then z is a minus mu over sigma, and when x is b, then z is b minus mu over sigma. And so that means now that we can also cancel the sigmas here, we realize that the probability that an arbitrary normal random variable is between a and b can be expressed as an integral of a density function that doesn't have any parameters, and the parameters have been pushed into the boundaries, which, I mean, it doesn't get us rid of the parameters. It shouldn't, because all of these are different distributions, certainly, but parameters in the boundaries are a whole lot easier to deal with than parameters inside the integrand, which is why this function has a special name, which is that if we have a continuous random variable z, that thing is going to be called standard normally distributed, or is said to have a standard normal distribution, if and only if its probability density function is this function from the previous panel, f0, 1, mu is 0, sigma is 1 of z, which is 1 over root 2 pi e to the negative z squared over 2. And in the presentations on numerical analysis, we have also gotten as close as we can in single variable to a proof that indeed this function is a probability density function, that indeed the integral of this function over the real line is 1. Okay, so now we can say the following. If we've got a normally distributed random variable with parameters mu and sigma, then the random variable z that is obtained by subtracting mu and dividing by sigma, that thing has a standard normal distribution, and the probability that our original random variable is between a and b is the probability that our normally distributed random variable is between a minus mu over sigma and b minus mu over sigma. The rule of thumb, essentially, that whenever we work with a normally distributed random variable, we will, in our computations, typically subtract the mu and divide by the sigma. That is something that will stay with us. In terms of proving this result, well, we already have shown the equation for the probabilities on 2 panels ago. We still would technically have to establish that this random variable z equals normal random variable minus mu divided by sigma has a standard normal distribution, but that's not that hard either, because the probability that this random variable minus mu divided by sigma is between a minus mu over sigma and b minus mu over sigma, that's the probability that the actual random variable is between a and b, and that is the integral of the standard normal distribution from one bound to the other bound, and these are exactly the bounds, which means if I wanted to make the algebra more complicated, I could now say c smaller equal this, smaller equal d, and I would get c and d right here. So this transformation really turns an arbitrary normal random variable into a standard normally distributed random variable. Okay, let's take a look at some examples, and basically we're going to talk about steel here for a while. And so let's consider an invented steel manufacturer who produces steel rods of a mean hardness of 68 Rockwell 2 units. Hardness of steel is measured in Rockwell units, which are dimensionless, and they come in 3 flavors: Rockwell 1, Rockwell 2, Rockwell 3. Rockwell 2 is the intermediate hardness, if you will, and values are typically around the 70s somewhere. So although this is a made-up problem, the units are something that is at least reasonable. It's something that an engineer wouldn't laugh me out of the room with. And let's also assume that the hardness of the rods is normally distributed with the above mean, 68 Rockwell units, Rockwell 2, and standard deviation sigma equals 2. I'm not sure how realistic such a large standard deviation is, but we can now start doing probability with that, because basically what you have to consider when you are manufacturing something, and especially when you're manufacturing raw materials, is that there is some kind of a scatter. And so what we want to find out here, for example, is what the probability is that a randomly chosen rod's hardness is at most 70. And well, that's just because the computation will work out nicely. Typically, you want to have that the hardness is at least something, because hardness for steel is a good property as long as it doesn't adversely affect the flexibility of the steel. Okay, so our random variable is the hardness, and so we want to know the probability that the hardness is less than or equal than 70. Well, the hardness is normally distributed with mean 68 and standard deviation 2, so we subtract the mean and divide by the standard deviation, and typically the way we will handle that is that on the random variable side we really subtract the symbolic quantities, whereas on the numerical side we subtract the numbers. Then we know that normal random variable minus its mean divided by sigma, that is a standard normal random variable, which is typically denoted by z. And well, the other part is insultingly easy, because 70 minus 68 divided by 2 is 1. Okay, so we need to figure out the probability that z is less than or equal than 1, and that's an integral, and it's an integral for which we don't have a nice antiderivative. And so typically people look up these numbers in normal distribution tables, such as this one, the cumulative standard normal distribution function, and we will also talk about cumulative distribution functions in the next presentation. This function records the area to the left of the value x that you put into the function, so it's the integral from negative infinity to x of the standard normal distribution. And so that means this entry here should give us the area to the left of 1, which is 0.8413. That may be a little small to see in the recording, but we're going to just go back here and we realize, okay, it's about 0.8413, so it's about an 84% chance that the hardness of a randomly chosen rod is at most 70 Rockwell 2 units. So the rule of thumb that will stay with us is we subtract the mu when we divide by the sigma, and we need to remember that the table gives the area to the left of the point, namely, and the picture that we would then want to draw is always that wherever our x is, the table gives us the area that is to the left of that x. That's what this one here gives us. I'm not sure if the scale is quite accurate, but as a generic picture for a normal distribution, that is pretty good. Okay, so now let's just stay with this and see what other kinds of probabilities we can compute. We could also determine the probability that a randomly chosen rod's hardness exceeds 71. Well, the story is the same. We just have to set up a different inequality, right? The probability of hardness greater than 71. We subtract mu, we divide by sigma. We do it symbolically for the random variable. We use the numbers on the side with the numbers. We end up with the probability that a standard normal random variable is greater than 3/2, and here we have a little bit of a problem because the table doesn't give us the probability that z is greater than 3/2. It only gives us the complementary probability, which is exactly this area here, right? And so one of the things that we're learning here is to work with complementary probabilities or with the fundamental theorem of calculus, because we realize that in order to get the area to the right of a value, we might as well work out the area to the left of that value and subtract that from 1. So the probability that z is greater than 3/2 is 1 minus the probability that z is less than or equal than 3/2. That probability, of course, we can figure out because 3/2 is 1.5, and so we end up with a probability of 0.9332 that we are to the left of 3/2. And when you do the subtraction, that means you've got 0.0668, a probability of 0.0668 to be to have a hardness that is greater than 71. All right, we keep staying with this, and now we want to know the probability that a randomly chosen rod's hardness is at most 67. Well, okay, the probability of the hardness less than or equal to 67, subtract mu, divide by sigma, we end up with a probability that a standard normally distributed random variable is less than or equal than -1/2. Again, we have a problem with the table in that the table only gives us values for z being greater than 0. Now, there are two ways around that, and in quite a few books you also have a table that includes negative values. I chose not to do that here because we can also use a little bit of symmetry, do some more graphical reasoning, play a little bit more with the meaning of the integral as an area. And so if I want to know the probability that z is less than or equal than -1/2, well, then I'm looking for a tail probability to the left of the y-axis. But because the standard normal distribution is symmetric across the y-axis, the probability that we're to the left of a negative x is the same as that we are to the right of the corresponding positive number. Here we have to be careful because if I start with a negative x and the positive number has a negative sign, right? But so basically that means that this probability is the probability of z being greater or equal than 1/2, and we know how to compute those because we can just go ahead and compute the 1 minus the probability of the complement, and well, the probability that z is smaller or equal than 0.5 is 0.6915 here, and so if we go back to that, we get 1 minus 0.6915, and so the result then is that the probability that the hardness is less than or equal to 67 is 0.3085. Okay, what else can we do? Well, we can figure out the probability that a randomly chosen rod's hardness is between two numbers if we have a certain range. Say somebody orders steel and says, look, it's supposed to be have at least a hardness of 63 and at most a hardness of 72, which may be determined by considerations that if you make steel too hard, it actually gets brittle. And with this process, that may, with whatever process is being used here, right, it's a fictitious setup, it may well be that too much hardness really introduces this kind of brittleness. Well, then we have to set up the probability that our random variable is between 66 and 72, which we do the same thing as before. We subtract mu and divide by sigma. It's just that now we have to do it on both sides. We have to do it for two numbers. Well, here we get -1 and here we get +2. So this is the probability that a standard normal random variable, which is that z here, is between -1 and 2. And of course we know now, if we look at that, if we're interested in the probability that a standard normal random variable is between a and b, we're interested in this area, which means we're interested in the area that we're to the left of b, the area that is to the left of b, which is the probability that z is smaller than 2, minus the area that is to the left of a, which is the probability that z is smaller than -1. And well, then we know that this is the probability of z smaller than 2 minus 1 minus the probability that z is smaller than 1, right? The same transformation as we did in the previous example. And well, then we just clean up the negative signs, and we've looked up stuff in the table often enough now, so we get that probability of z smaller than 2 is 0.9772. The probability of z smaller than 1 is 0.8413, and if we add those two numbers and subtract 1 off of it, we get 0.8185. So we've got an 81% chance that we are within this range, which presumably would be the good range here. Alright, I think this should now be the final problem in this setup of examples, where we're still with the same steel manufacturer, and well, basically in manufacturing processes you've got to have ways to influence your product, and we can't go into the details of what that would mean for manufacturing steel. That's a separate class, but basically there's got to be a way to adjust the mean hardness by adding various different kinds of elements, different kinds of metals to the steel. And so then a natural question would be, if you've got an order that everything you make, or at least a lot of what you make, has to exceed a hardness of 68, how do you have to choose the mean so that you've got a 90% probability that a randomly chosen rod has hardness of at least 68? Well, that would mean that we are interested in the probability that the hardness is greater than 68, but we have to set that equal to 0.9. Okay, well, still, same story. We subtract the mu, divide by the sigma. It's just that this time we don't know what the mu is, right? And, well, when you don't know what the mu is, you just keep it as a variable. And, well, we have an equation here that now says that a standard normally distributed random variable needs the probability that that thing is greater than this number is supposed to be 0.9. Well, let's take a look at the table. And the entry 0.9 is achieved somewhere around here, right? That's about 0.9, so that's 0.8997, which is achieved for 1.2 and then 1.28 apparently. And so yeah, that's what we have to find here. And okay, I've made a mistake with the inequality. If the area to the right of our number is 0.9, well, then that would mean that the area to the left of the negative number is supposed to be 0.9. And now we get the 1.28, and so the probability of z being smaller than 1.28 is approximately 0.8997. We can't get an exact match, at least with the table, and that's typically overkill anyway. But basically what that means is that negative 68 minus mu divided by 2 needs to be equal to approximately 1.28, and that's now an equation that we can solve. So negative 68 minus mu divided by 2, we set that equal to 1.28. That means 68 minus mu is negative 2.56, and then we subtract, we add mu and add the 2.56, and we end up with mu being 68 plus 2.56. Well, that's 70.56, and as a quick sanity check, if we want that the area to the right of 68 is about 0.9, then we definitely need a mean that is to the right of 68, and 70.56 looks fairly good for that. Okay, so something that you may need for the homework: if you've got a standard normal random variable, then for any alpha between 0 and 1, the number z alpha denotes the value such that the probability z greater than z alpha is alpha. That is, alpha of the area under the standard normal curve lies to the right of z alpha, and so the picture is that if this area is alpha, then this cutoff is z alpha. We will need these values when we talk about confidence intervals, and it's basically one of those things for a lot of things, and especially also for the custom for working with cumulative distributions. We're interested in the area to the left of the number. Well, here we're talking now about the area to the right of the number, which every so often we also need. Okay, final properties. If you've got a normally distributed random variable with parameters mu and sigma, then the following properties hold. The probability that x is within one standard deviation of the mean is 0.68. The probability that x is within 2 standard deviations of the mean is about 0.95, and the probability that x is within 3 standard deviations of the mean is about 0.997. You may have seen these probabilities: 68%, 95%, and 99.7%. You may have seen or heard about these probabilities in labs before, because basically when in a lab you compute your sample average and your standard error, then people often say, not quite correctly, that you've got a 68% chance that your actual value is within 1 standard error of what you measured, a 95% chance that it's within 2 standard errors, and a 99.7% chance that it's within 3 standard errors. So now this is something where we're starting to connect to stuff that you may well have already seen in labs. Basically, this is the probabilistic justification. In order to fully understand what that language means, we will talk about confidence intervals, but basically let's just talk about where these probabilities come from. They come from the fact that there is a certain reasonable assumption that certain things that you measure in the lab are normally distributed. And well, then that means that we would really end up with these kinds of probabilities. And the way you compute these probabilities is actually fairly simple. If you're interested in the probability that mu minus k sigma is smaller than x is smaller than mu plus k sigma, which is exactly what we have here with k equals 1, 2, and 3, well, then you subtract mu, you divide by sigma, right? And that means your x minus mu over sigma is a z. And from the other computations, you're only keeping a minus k on the left and a k on the right. So that's just straight algebra. And well, that's then with the transformations we had, that's probability of z smaller than k minus probability of z smaller negative k, which is the probability of z smaller k minus 1 minus the probability of z smaller than k, right? We're just using the flip and then the complementary probability. And that's 2 probabilities z smaller than k minus 1. And if we now just work out the numbers, which we can look up in the table, we end up with approximately 0.68 for k equals 1. We end up with approximately 0.95 for k equals 2. And we end up with approximately 0.997 for k equals 3. And that basically proves that these probabilities really are what they are claimed to be. And so that means, and this is really just a picture that we're finishing with, in a normal distribution, you have a 68% chance to be within 1 standard deviation of the mean, a 95% chance to get an outcome that is within 2 standard deviations of the mean, and a 99.7% chance to get an outcome that is within 3 standard deviations of the mean. We will become a lot more familiar with normal distributions as we continue, because they will come back to us, for example, in the central limit theorem. The numbers themselves are right now just background information. They apparently have something to do with things that you'll measure in the lab, and we'll see what the exact connection is later on. For now, you have three families of probability density functions that you can compute probabilities for. And so let's get to that. Let's have you compute some probabilities. Thank you.